Feature scaling is more, actually all of them under feature transformation. So if you don't want like to have confusion about specifying them, all of them, after all, they are feature transformation. Why? Because they are changing the current values to new values. They are numeric attributes. They already have some values like age. Let's say my age is 20. Then I'm applying feature scaling or transformation. What I'm doing, I'm changing 20 to some other new value, right? So after all, feature scaling is feature transformation in general, okay? Now, since both here, just giving you an example to understand why scaling can be important or transforming the data can be important. So if you look into these two columns, we have two numeric attributes, okay? Now, the range for CGPA is between 0 and 5, correct? While the salary might be much greater. As I said, some algorithms are sensitive, or the quality of their results will be affected because of their sensitivity, okay? So in this case, we need to ensure that they don't have that much sensitivity. So what we do, we need to scale all their values, all the numeric features, to ensure that all the features contribute equally to the results, or they have equal footing. I like this term. They have equal footing, okay? Now, this example here, we applied here standardization. We applied here standardization, this one. The example showing you standardization output, okay? So we have standardization, we have normalization, and you have different classes inside scikit-learn you can use. So we're going to talk about max ABS scalar, min-max, and z-score normalization or standardization. Okay, so min-max scaling, we already discussed about during practical session, right? So the equation is simply where we are changing each old value by subtracting it with xmin divided by xmax minus xmin, and then we get a new value. So we substitute or replace the existing value by x new. Each x old is going to be replaced by x new. Now, overall, min-max will give you scales between 0 and 1. Okay, the output of min-max, if you apply this mathematical operation, will give you values between 0 and 1, and it is sensitive to outliers. Okay, why it's sensitive? Because as said, if you look to the equation, it has considered xmin and xmax. So outliers usually resided at the extreme places, either maximum value or minimum value. So in this case, while you are doing transformation process, you are considering the outliers all the time. So x new is going to be affected with the outliers. So in other words, if you suspect your data has a lot of outliers, don't apply min-max scalar. Okay? If you check your data and you found that you have a lot of outliers are a lot, then don't apply min-max scalar. Okay? Because min-max scalar is going to generate new values which are affected by the outliers. Okay, like virus. It has considered the virus inside the data, generating a new data or new protein or whatever with viruses. Okay. How about max APS scaling? Max APX scaling actually is similar to min-max, but it's special when xmin equals 0. So in other words, max APS scaling is same as min-max scaling when xmin is 0. Okay? So it's a special case of min-max where xmin is 0. We check our data like CGPA, then xmin is 0. Or like if you are working on computer vision, the pixels, the lowest value is 0. So same. So in this case, what do you do? Shall we apply xmin, xmax? Up to you. Either you go ahead, which actually will result same like max APS scaling. However, since xmin is 0, so if you check here the equation, xmin is gone. Xmin divided by xmin, right, has gone, has no impact now because since xmin is 0. the scale will come different this time. It's gonna become between -1 and +1. Okay. In other words, if features all values are positive, then it's gonna give you a positive scale between 0 and 1. If features are all negative, then your scale is gonna be between -1 and 0. It is still sensitive to outliers because X-min is there. X-max is there, right? X-max is still there. So it is sensitive to outliers and works on positive value if you want. But again, as we said here, it can work on negative if you are okay to have between -1 and +1. Okay, for max APS scalar, you have special class in scikit-learn called max APS scalar. Okay. Standardization or z-score normalization. Normalization for z-score, we're talking about standardization, in other words, is more radical transformation. Why it's more radical? More radical because it is going to change not only the values of the features to new values, but also the distribution of the data. While the previous one, they may not replace or change the distribution, just you are changing the values. This one is more radical because it has done two things. It has changed the values to new values, plus it has changed the distribution of the data. Okay, usually the scale is between the output between -3 and +3, but as I said here, not necessary. That means it's possible to get output, let's say -4 or +5. It's possible. Okay, standardized values always have the mean of 0, and we already proved that, if you remember last session, where we got value of mean very small, 0.000000, then some other values. So the mean should be 0 and standard deviation is 1. Now, standardization doesn't transform to predefined scale. If you like to use predefined scale, like 0 and 1, then cannot apply standardization, because standardization has, as we said, the output, the scale is between -3 plus 3. Okay, standardization is much less affected by outliers, okay? But not completely unaffected. It's much less affected. Why? Because if you check the equation, it doesn't have X-min and X-max. However, if you check X-mean is going to consider the outlier, but the impact should be much less because it's not the only outliers we are calculating the mean for. We are calculating mean for the entire data set, okay? Clear? Any question? By the way, this scalar or this is also useful to identify outliers. This is also useful to identify outliers because if you check here, what just now we said, okay, approximately it has value between -3 plus 3, right? Now, as said, values can be lower, -4, or can be higher, like let's say +4 or +5. But in case you got these values, this is an indication of outliers. So meaning any value of z-score that lies outside the scale or the range between -3 plus 3, okay, here can be considered as outliers. Okay, so this scale, this transformer is also useful to find out outliers. Why? Because if you remember back to the normal distribution, since it has changed the distribution to have mean of 0 instead of deviation of 1, right? If you remember from another figure during data understanding, I think there was one figure talking about normal distribution. All right. So if you check here, what it says, mean, and then mean plus 1 standard deviation, mean plus 2 standard deviation, mean plus 3 standard deviation, right? So any values reside outside can be considered outliers, okay? So same case is there. If you got values that is, in that case, standardization mean should be 0, and this one should be mu plus 1, here plus 2, here plus 3, here mu minus 1, mu minus 2, mu minus 3. So any value that resides outside, we can consider it as outliers. Okay? Okay, so here's summarization for what we have discussed. So under standardization, we have z-score. Robust scaling, I'm not talking about it here, but if you're interested, you can look at it, which also can be useful when you have outliers. So again, if you have a lot of outliers, you may look for z-score, you may look for robust scaling. So don't use min-max or ABS if you have a lot of outliers inside your data. And you're not treating them, you're not removing them, you're keeping them, okay? So z-score, you look for normal suitable for algorithms that assumes normal distribution. So already given to you here, not suitable for sparse data. So again, if you have also sparse data, this transformation is not so useful. These are some of the algorithm can be useful for z-score. Robust scaling, when outliers are present, then also robust scaling is good. Okay, you can apply. Min-max, when standard deviation is small. Okay, when distribution is not normal or unknown, you don't care about it. Okay, not suitable when outliers are present, as we just discussed earlier. These are some of the algorithms that this can be suitable for. Max is designed for scaling sparse data. Why? Because actually it's already considered X min is 0. It's not there. So only it's taking X max. But anyway, same like the old one, is sensitive to outliers. Okay, so all normalization generally are sensitive to outliers. So keep that in mind. So this is why you see when you are working on data preparation and data understanding, how it may take a lot of time. Because let's say modeling, you're not happy. Then you go check, remember, oh, I have a lot of outliers. So now I may go and remove the outliers or treat them. Or maybe I change the feature transformer. Or you keep trying. So it's actually more like trial and error. You keep trying, changing, run again, try. So actually feature, data understanding feature, data preparation can take a huge amount of your time. Okay. So some algorithms that require features to be scaled, which are sensitive, as discussed. These are the sensitive algorithms. These are sensitive toward the scales of the feature, meaning if you have feature with great scale, big scale, another feature with small scale, these algorithms are sensitive. Okay? Linear regression, logistic, neural network, principal component analysis, and all distance-based algorithm. Any algorithm that calculates the distance is also can be affected. Here, just giving you some example like K nearest neighbor, K means support vector machine, and others. While those tree-based algorithms, usually they are insensitive. Any algorithm that depends on the data structure of a tree, usually it's not sensitive. Like decision tree, random forest gradient boosting. Those algorithms are not sensitive or less sensitive toward the scales of the features. Meaning, maybe someone will ask, what would happen if I apply feature scaling for tree-based algorithm? Maybe nothing. If you apply or not, the results may still same, or maybe slightly different. Okay, while this one, no, you may have big impact whether the scale is, the scale are similar or not similar because they are sensitive. Okay, so you still can try. Let's say you are using tree-based and anyway you like to try it, then see whether the results have increased or not. But simply or as a rule of thumb, these algorithms are insensitive toward the scales. As with all the transformation, it is important to fit the scalars to the training data only. This is very important. Remember, the data, the training data is historical data supposed to give you an idea about the distribution, right, of your data, about other things as well. So if you are applying transformation, let's say min-max scalar, you decided to go with min-max scalar, then where you fit your min-max, because always you need to fit, then you apply transform. Remember, when we work with transformer in scikit-learn, we have two functions, fit, right, and we have transform, right? Right or left? Left, okay. Well, if we are working on prediction, like let's say k-means or those algorithms, let's say KNN, then we have fit and predict. correct? We have two functions for those algorithms. If you are working on transformer, then you have fit and transform. Now, where you fit your transformer, or even you fit your model on the training data, okay? Only. So fit function must only be called with training data. Now, when the time comes to transform your data, let's say on the test set, okay, then do you call fit on the test set in order to find the values that for X-min and X-max, let's say if we are using no. So X-min, X-max, in other words, has been fitted and found from the training data set. Just we use them to transform any other data, including test set, including unseen data, including future data, including whatever data. Okay, so you fit only on the training set, not on the full data set. Only then you can use them to transform the training set and the test set into the new data. So transformation applied to all, but fitting applied only to training data. Okay,